As semiconductor processes shrink, the three chip giants, TSMC, Intel, and Samsung, are pushing for advanced tech. They are developing a new transistor, CFET. What exactly is the CFET design? CFET means complementary FET. It is seen as the next-gen GAAFET technology. It mainly uses 3D stacking for 2nm processes and below. Before CFET, let's briefly review past scaling tech to better understand how these technologies evolved. A semiconductor has conductivity between an insulator and a conductor. It's important because we must control whether it conducts electricity. As the process shrinks, maintaining this control gets harder. Thus, technology must advance. MOSFET is the most common transistor used widely in analog and digital circuits. The general operating principle of a MOSFET is that electrons flow in from the source on the left, pass through the electron channel beneath the gate, and flow out from the drain on the right. The central gate controls whether electrons pass underneath. Below the gate is a thin oxide layer. The name MOS comes from the vertical layers: metal, oxide, semiconductor. When the gate length shrinks below 20 nanometers, electrons can sneak past, causing leakage. Also, as the gate length shrinks, the contact area with the channel below decreases. The goal of process scaling is to solve leakage and increase gate contact area. Let's look at the differences between MOSFET, FinFET, and GAAFET. The channel placement changes to increase contact with the gate. When the process shrinks to about 16 nanometers, it shifts to FinFET. It changes from a 2D planar design to a 3D structure, standing the source and drain up to increase contact area with the metal gate. Since the upright structure resembles a fin, it's called FinFET. FinFET reduces the transistor footprint. The channel is surrounded by the gate on three sides, increasing control and reducing leakage. However, below 3 nanometers, physical limits are met, so Samsung moved early to the next step, Gate-All-Around FET, or GAAFET. TSMC's 3 nanometer still uses FinFET, but leakage starts below 3 nanometers. So, FinFET is shifting to GAAFET. By changing the fin from vertical to horizontal, this increases contact area. Samsung's 3 nanometer GAAFET design is called MBC-FET. It's similar to FinFET, GAAFET surrounded by the gate on 4 sides, while FinFET only has 3. GAAFET also splits into nanosheet and nanowire structures. Nanosheet uses wider, thinner fins wrapped by the gate. Nanowire uses wires to increase the semiconductor area, then wrapped by the gate. TSMC and Samsung currently use nanosheet GAAFET. Samsung announced 3 nanometer GAA MBC FET progress last year. MBC FET offers better design flexibility by horizontally stacking the fins. It allows free adjustment of nanosheet height and wider channel choices than FinFET. TSMC's roadmap suggests the next step after nanosheet is CFET, carbon nanotubes, or 2D materials. TSMC reports breakthroughs aiming for further size and power scaling. Now let's discuss CFET. CFET, or complementary FET, is the vertical stacking of NMOS and PMOS. This technique stacks different materials like silicon and germanium vertically. It brings P-type and N-type transistors closer, eliminating the N to P separation bottleneck. CFET reduces the cell active area by half. The industry expects CFET commercialization to take 7 to 10 years. Much preparatory work is still needed. Reports suggest CFET is the most likely successor to GAA within 10 years for 2 nanometer nodes and below. Interestingly, IMEC's roadmap shows GAA has nanosheet, forksheet, and then CFET. But recent production status suggests process evolution has slowed. Let's look at CFET progress from Intel, Samsung, and TSMC. Intel demonstrated the simplest CFET circuit, inverter, last year. Intel shared several improvements, noting the inverter is done on a single fin, a single CFET. Size is half of current CMOS inverters. Intel likened past chip tech to pizza, layered from the bottom up, starting with transistors, building wiring layers, and finally flipping and packaging. As transistors shrink and density increases, wiring complexity grows, leading to more layers. It takes 10 to 20 layers to power and signal the transistors below. Therefore, Intel is studying backside power delivery, or BSPDN. This tech places interconnects above and below the silicon surface. Intel also showed CFET scaled to 60 nanometer gate pitch, combining 3D stacking with backside power and contact tech. Samsung calls CFET 3D FET. Its demonstrated solution has a 45 to 48 nanometer gate pitch. This is smaller than Intel's 60 nanometers. Samsung aims to isolate electrically the stacked PFET and NFET to prevent current leakage. This uses a new dry edge tech to replace wet edge. The dry edge helps increase device yield by 80%. Unlike Intel's 3 nanosheet per transistor approach, Samsung uses single nanosheet per transistor pair. TSMC's gate pitch is also 48 nanometers. Its CFET solution forms a new dielectric layer between top and bottom transistors to maintain spacing. Nanosheets are layers of silicon and silicon germanium. TSMC is testing a specialized silicon germanium etch method to build isolation layers before exposing the silicon nanowires. In summary, CFET commercialization is expected to take 7 to 10 years. Will this timeline be met, delayed, or accelerated? We shall wait and see.